Jonathan, I believe you have a filter turned on in the video settings. You might want to.
Yeah, we're trying to. Can you hear me, Professor?
Yeah, I can hear you. I think it's a filter.
Yeah, it is. And I don't know how to remove it, eh? I've got my flatmate here, and he's trying to, but, well, I guess I'm prepared to go forward with it. I'm here live. I'm not a cat.
Yeah, I can see that. All right, let's go to the next student while you sort it out, and you can try again later.
Oh, never mind the marks. Oh man, Kev, I just did the projections. If Schrodinger catches me, it's 50% likely I'm going to be killed, eh?
Yeah, I think Jono's cactus somehow. Lecture 4 is on operators, and just to recap where we're at the moment, we've spent the last two lectures building a little bit of a mathematical framework for quantum mechanics. And the way we've done that is to build ourselves an n-dimensional complex vector space that we call a Hilbert space, with a number of dimensions equal to the number of measurable outcomes. And so for our quantum spin, we have two-dimensional complex vector space. What we've done is set it up so that there's a vector that represents the state of a system. We call it a state vector. And then the basis vectors for that space are basically the possible measurable outcomes that you would have for a measurement, okay? And in the last lecture, what we looked at was how to obtain the probability for the outcome of a particular measurement. And we obtain that probability essentially by taking a projection of the state vector onto a basis vector, which corresponds to the outcome of that measurement. Okay, so what we've built up so far is an architecture for handling the state of a system and working out the probability of the outcome of a measurement. Where I want to go today is to introduce another piece of this mathematical framework, and it's a piece called operators. As the name suggests, it's the thing that does operations. Okay, so let's bring up some slides. Operators, to start with, nice little sort of pun here, are all matrices in quantum mechanics. So basic idea is that you treat the states of your system and the measurable outcomes as vectors, and the way you sort of operate on those vectors is by using matrices, and those matrices, when multiplied with vectors, will change the vector to something else. Okay, so there's a whole pile of operators in quantum mechanics, and we saw one of them yesterday, this projection operator. So basically it's a matrix that enables you to get probabilities out. And we also discussed a different one yesterday when we were talking about changing the basis for a measurement, which would be a rotation operator. So essentially a matrix that enables you to switch your basis states from one particular measurement that you're interested in, like the projection of the spin along X, to the other one, another one you might be interested in, which is the projection of spin along Y or Z, for example. Okay. There's a big class of operators in quantum mechanics, and some small subset of those are all linked to observables. Okay, so everything that you can observe as an outcome for your quantum mechanical system will have an operator attached to it, and that operator will be an n by n matrix where n is the Hilbert space dimension. So to give you one example right now, you can imagine the measurement of projection of spin along the z direction is it's an observable. It's a thing that we can measure. It will have an operator connected to it, and as we'll see in the lectures that follow this one, it's an operator called sigma z, and it has a matrix. We're in a two-dimensional Hilbert space, so it's a 2x2 matrix, and that thing represents that measurement, and it does things to vectors. Okay, we'll talk a little bit more about exactly how that works as we go forward. What I want to start out with today is, first, I want to just look at properties of operators in general. I want to define what an eigenvalue and an eigenvector is very quickly so that we have this for coming lectures. I want to look at what it means for operators to be Hermitian, because this is something that's quite important in quantum mechanics. We'll look at what the implications of Hermitian operators are for eigenvalues right at the end of the first half. So this first half of the lecture might be a little bit longer than the second half. And then in the second half, I want to come back and look at expectation value as an example of using operators in some sensible way. Okay, and this will set us up for lectures 5 and 6, where we sort of start building up how do we deal with quantum mechanics as a bigger picture for spins before we then change topic to a few other things. Okay, so we're maybe now 3 lectures away from having a very, very complete picture of what quantum mechanics looks like as a mathematical framework for a simple system like a spin. Okay, so operators are matrices. They operate on state vectors, and when they do so, they produce a new state vector. So to look at this just from a mathematical perspective, what we have is some matrix M. We multiply it by some ket A, and that will give us some new ket B. Okay. Now, again, we're having to work our way through subsets here. So not every matrix M is a linear operator. So and the reason why we care about that is that if in order to keep the mathematics well behaved for quantum mechanics, we actually want to stick with linear operators. So what we do here is basically restrict ourselves to the subset of matrices that are linear operators. What that means is, of importance at least, is the linear operator must give a unique output for every vector in the space. Okay. We don't want to have a situation where an operator gives you, multiple answers, or worse, is it irreversible? When a linear operator acts on a vector, it gives the same multiple of the output vector as when you've got a number multiplied by a vector. So in a sense that it doesn't do weird things based on the size of the vector. And one other property that's kind of important is that it obeys the relation where if the matrix operator is operating on the sum of 2 vectors, then that's the same as the operator acting on the 2 vectors independently and then adding them together. Okay, so these 3 requirements, they're not really something you have to learn by rote and be able to write them down on the page, but you kind of want them in the back of your mind so that you know the difference between something that's going to be well behaved and something that's not going to be well behaved, so that you don't end up going into crazy places with mathematics. Okay, and a lot of these are just general rules that you kind of know hold for mathematics in such a way that you can spot when things look wrong. Okay, that's probably the best way to put the importance of them. Okay, so I'm kind of expected you all to come in with a little bit of linear algebra background, but in this lecture in particular, I'm going to highlight 3 things just to make sure everyone's on the same page with them. The first 2 are how matrix multiplication works. And the first one should be really obvious because you've probably done this before in your linear algebra courses. So if you take a matrix M and you multiply it by a column vector, and here I've made them 3 by 3 rather than 2 by 2, just so that it's really clear how this works. Okay, so I always have sort of like a hand mnemonic to remember how the multiplication goes for this, and it's basically pick up the top row and put it onto the column, and that gives you the top element. Pick up the second row, put that onto the column, and that gives you the second element. Pick up the bottom column, put that onto the column, and that gives you the third element. So what you can see here is this would be, to work through the first one, m11 times alpha 1 plus m12 times alpha 2 plus m13 times alpha 3 gives you beta 1. And you can see that in the first equation at the top. Okay, if you're not familiar with it, work your way through it. If you're familiar with it, excellent. The reason why I wanted to point that out is that a lot of people are not familiar with the way you need to do the multiplication for when you're dealing with bras, okay? And this is important because there's an aspect here not just of conjugation, but there's an aspect of the order that you do the mathematics when you write these things, okay? And so if you go along in quantum mechanics, you'll very rarely see the operator M put in front of a bra. It's usually on the right-hand side of the bra. And so in a sense, this long bracket here is almost part of the notation from the perspective of pointing to where things should go relative to that vector. Okay, so this is always the way I remember how to put things in various places as I work my way through. Okay, so you'll more likely see it in this form. Multiplication of the bra A with the matrix M will give you some new bra B. Okay, and if we look at this from this perspective, and for the moment, just ignore the fact that this matrix is conjugated. We'll talk about how we do conjugates of matrices in a moment. I just want to look at how the elements pop out of this thing very quickly. So here, I actually sort of don't really like using this version of it because it's hard for me to remember, but I still use this same picking up idea. So you pick up the row and you drop it onto the first column, and that will give you the first element, right? And so you take this one, second row gets you the second element, this one, that one, right? So in both of the versions of multiplication, you're going from one to the other, okay? So let's just work through this. This would be alpha 1 conjugate times M11 plus alpha 2 times M21, and you can see that in here, and alpha 3 times M31, which is this one here, okay? You'll get the wrong answer. Okay, we'll come back to how this works when we talk about conjugation for matrices in a few moments. Okay, so that's matrix multiplication. We know what an operator is. An operator basically just is a matrix times a vector, which gives you a new vector. Okay, one thing that we really care about for operators, particularly for any operator that's connected to an observable, so the ones that are connected to the things that we measure, is what the eigenvalues and eigenvectors are, okay? Now, in general, an operator M will give you a new state vector that points in a different direction to the original state vector A, okay? So if I just take some random matrix, acted on some vector A, I'll get some vector B, completely arbitrary, and it should point in, whatever direction it points in once I've done that multiplication. And you can sit down for yourself and find yourself examples. They're pretty easy to write because if you just chuck random numbers in, you should get this behavior. You should be able to show that A and B generally don't point along the same direction. The special thing about eigenvectors and eigenvalues essentially is that when you take a matrix M, if the vector that M operates on is an eigenvector, what you will get back is that eigenvector multiplied by a number, okay? And that number, in our particular case here, will be a complex number, so that's perfectly fine. What the geometric meaning I often take away from this is that the matrix operating on that vector basically takes that vector and keeps it pointing in the same, if you think about it in a real space for a second, so imagine that lambda is real, it keeps that vector pointing in the same direction, and it either makes it longer by lambda or shorter by lambda if lambda is less than 1, or if lambda is negative, it basically just points it in the other direction, okay? So this is, for me, is sort of geometrically what's going on in the Hilbert space that's special about eigenvectors. It essentially conserves direction. When you go to complex numbers, it gets a bit more difficult to visualize because you're actually in a space where you've got complex amplitudes. And so seeing it like that is a little more difficult to do in your head. Okay, so this vector here that basically comes out multiplied by a number when you operate is a thing we call an eigenvector. And the number that multiplies in here is a thing we call the corresponding eigenvalue, okay? Right. One more piece of naming that I'll use in here. Sometimes the set of all the eigenvalues for a given operator will be called the spectrum, okay? And one thing that you'll quickly realize as you work through is that for an n by n matrix, there will be up to n independent eigenvalues. Okay, sometimes there'll be two eigenvalues that are the same, and we'll talk about what that means in another lecture. But generally, there will not be more than n eigenvalues for a matrix that's got n by n dimensions. Okay, that set of up to n eigenvalues is a thing that we call the spectrum, and the reason we call the spectrum is a historical thing. Later on, when we get to infinite square potential well, you'll see that energy levels or discrete energy levels, just like you get in an atom, are essentially eigenvalues. And so that is an energy spectrum. It's a set of allowed energies. And because they correspond to eigenvalues, and this is where it first came out, people call that set of eigenvalues a spectrum. Okay, just so you know where that comes from. Okay. One last point on this is that the eigenvector for an operator M is not necessarily the eigenvector for an operator N. Okay, so different operators and different matrices have different eigenvectors. That doesn't mean they can't be the same. It just means that the eigenvector for one is not necessarily the eigenvector for another. So for any independent operator you care about, if you want to know what its eigenvectors are, you have to work out what they are for that matrix. What they are for something else is entirely irrelevant. Okay, so case-by-case basis. Okay, most of you know how to get eigenvalues. You probably know how to do it better than I do because you've just finished math courses. But just in case you haven't, I'm going to go step through this super quickly. We'll deal with it in tutorials. You'll deal with it in all the problems you do through the course. And if we need to, we can come at it in one of the Friday workshop sessions. But basically, you have a matrix, and there's 3 steps to getting eigenvalues. The first is that you subtract lambda times the identity matrix from it. So you basically get a matrix that looks like this. Then you take the determinant of that matrix and set it equal to 0. That will give you for a 2x2 matrix, a quadratic in the possible eigenvalues. If it's a 3x3 matrix, it's a cubic. If it's an n-by-n matrix, it's a massive equation that's difficult to solve. And then what you do is you go through and solve that equation, and it will spit out the eigenvalues. Okay, so in this particular case, you'll get 2 eigenvalues, -2 and -3 for this particular matrix up here. Okay, I'll let you try that for yourself and prove that it works, and then you should do heaps of examples of this, because pretty much guarantee every exam I ever give, there's a get me some eigenvalues questions in there. Okay. One nice little piece of observation in here is that you'll notice that the sum of the eigenvalues is equal to what we call the trace, which is just the sum of the diagonal elements in the original matrix, right? That is often a really useful trick for sort of working out what the solutions are to the eigenvalues. For a quadratic, it's not very hard because quadratics are easy to solve. When you have to deal with 3x3 matrices and you have to solve cubics, that's when having some idea of what the factors might be helps you sort of split the cubic into a quadratic plus another term and then work from there. So that trace, idea of the trace being the sum of the eigenvalues is a very useful thing to keep in your mind. Okay, so I'm going to dedicate a whole slide to this point because it's an important point, which is why do we care about eigenvalues? For the class of operators that correspond to measurements, eigenvalues are particularly important. And they're particularly important because what they tell you is what the outcomes of the possible measurement are. Okay, so let's imagine we want the operator associated with measuring the projection of the spin along Z. We know there's 2 possible outcomes, +1 and -1, right? And when we build this matrix, which we'll do in one of the next 2 lectures, we will find basically that the eigenvalues of that matrix are +1 and -1. Okay, so they're the measurable outcomes. And this is why we care so much about eigenvalues. It's also why we care so much about eigenvectors, because as you'll see, those are actually your basis states for the system. Okay, all right. So one of the real things that's important about matrices is doing conjugation properly. So if you remember back to lecture 2 when we talked about the key properties of bras and kets, we had this little 0.8 at the end, and I actually stopped on it briefly because it's one of those ones that's, you know, not just maths being well behaved, but one that you might not expect to see, and one that's very important because if you don't get it right, everything goes wrong. And it was basically that if you take a complex number and multiply it by a ket, and you want to consider the equivalent bra for that, it's not bra A times Z, it's bra A times Z conjugate. Okay, and so the idea here was that when you conjugate, you conjugate everything. If there's a number out front of the vector and you're switching over to the to the equivalent conjugate, you conjugate the number as well as the vector. The same thing holds for matrices, because essentially in quantum mechanics, any matrix is going to be a matrix of complex numbers, right? And if you're doing it for one complex number, you have to do it for the whole matrix of complex numbers. That's fine. The thing is that the simplest option you can think of here, which is just take matrix and take the complex conjugate of every single number in that matrix, does not work, okay? There's something more that you have to do. So when you take that complex conjugate, it's usually a thing that we call M dagger, and I'll show you why that's called a dagger in a moment, and it's not a star, because that dagger is there to tell us that we do something more than just take the conjugate of each of the elements, okay? All right, so in my exercise notes on the website, there will be a bit of maths on proving that Hermitian conjugates are required for quantum mechanics. I used to do this in the lectures, and it would take me 20 minutes of just working through matrix elements, and I'd bore everyone to death with it. I'm going to let you work on that for yourself as an exercise, because actually it's kind of useful for you to dig into the maths and see it for yourself. And you'll have my fully worked solutions for it. I'm actually just going to talk my way through it, because you can kind of see it in the slides I've already done how this will work, okay? So let's just pop back to matrix multiplication for a moment. What you will notice in here is that if we take the matrix and we multiply it by the ket, what we're actually doing is we're taking this top row here, and it is becoming the thing that goes into that first element, right? And then here it's the second row that goes into the second element, and then the third row that goes into the third element. So we're basically taking slices like this. If you now jump across to handling bras, what you'll notice is we're not actually taking the rows anymore. We're actually taking the columns, right? So what you want to do in taking, in going from the ket side to the bra side to deal with that conjugation properly is not just take the conjugate of all the elements, but you also want to transpose that matrix. You want to take all the rows and turn them into columns, so that you handle the fact that in a ket, you go from a column vector to a row vector, with this side being the numbers and this side being the conjugate, right? So when you go from one side to the other, you're basically doing a transpose and you're doing conjugate of everything. And you have to do the same thing with the matrices. So you take the matrix, you transpose it, you go from columns to rows, and take all the elements. And if you sort of think this back to the complex number, you can kind of see a complex number as just a 1-by-1 matrix, right? So you take that complex number out the front, you transpose that 1-by-1 matrix, which means it stays the same, and you take the conjugate of it, right? So as a general rule, all the way through quantum mechanics, whether it's scalars or vectors or matrices, if you're going from the ket side to the bra side, you're taking the transpose of it and the conjugate of all the elements, okay? And I'm really here just seeing a vector as a 1/n matrix. And this is why you sort of got my meme at the start. In quantum mechanics, everything is a matrix. It's just that vectors have only 1/n, and a scalar is just 1/1 matrix, okay? Everything's a matrix. All right, so just to recap this is the main reason why we have the dagger here for the matrix and not just the star, because what we're actually doing is taking the transpose and the conjugate, and to give you a symbol that doesn't look like a T and doesn't look like a star, we just go to a dagger. It's like a hybrid of the two, okay? So always remember this: if you're getting the conjugate of a matrix, interchange the rows and columns, complex conjugate of all the elements, okay? And so for a matrix M, if M times A gives you B, then if you want the bra for B, the way to get it is to multiply the bra A by the matrix M dagger, okay? And this is the thing usually known as Hermitian conjugation. All right. Now, the next thing I have to cover is what it means to be Hermitian. And what we're going to do in quantum mechanics generally is is find that every single matrix we ever deal with is Hermitian, which basically means that a matrix L is equal to its own Hermitian conjugate, right? And this is why often you will see not necessarily M dagger here written, but M. And this is often just people being a little bit sloppy about this. You can do that simply because you know for pretty much every useful operator in quantum mechanics that the matrix is equal to its Hermitian conjugate, and so you can kind of use it interchangeably. Okay, so this is where we sort of get a little bit down in the work, a little bit sloppy about our notation all the way through. Some of you will go, well, why do we want Hermitian matrices? I'll show you in a few minutes why we want them. And I guess another question is, do we absolutely need Hermitian matrices? For most of quantum mechanics, yes. But just to give you some perspective for just broader, bigger picture, there's a whole class of research goes into non-Hermitian quantum mechanics and sort of, how do you make theories for quantum mechanics where this rule of L equals L dagger does not hold, and is that useful for things? And so there's a whole separate area of science where people look at these sorts of problems and try to develop theories where that works. And it works for some subsets of problems. If you go and if you're really curious and you're interested, you can go and have a look at it. It's actually a useful approach. But for pretty much everything you do in standard quantum mechanics all the way through undergrad, and even a lot of sort of what you do in a real career in physics, we pretty much limit ourselves to Hermitian matrices. Okay. All right. So some key properties of Hermitian matrices, just quickly, so you know them. Some key properties of Hermitian matrices are that they can be written in a form where, and I read off my own slide there because I want to be very careful about the words, they can be written in a form where. One thing you'll know from your first year maths courses, hopefully, is that you can take a matrix and you can perform a series of transformations on it so that essentially it's the same matrix, but the elements are different, okay? And what that means is that a matrix that is Hermitian and can be written in a form where this is obvious may sometimes actually be in a form that doesn't give you this. And that doesn't mean it's not Hermitian. It just means that it hasn't been transformed to a version where you see this yet, okay? But in a lot of cases, you can get Hermitian matrices to a form where the following things hold. First is that the diagonal elements are real, okay, because they need to be their own complex conjugate. When you do a transpose of a matrix, the elements on the diagonal are kind of unique in the sense that they stay in the same place, right? If you take a row and a column, if you take the row to the column, the one that's on the diagonal will be the one that stays in the same place, okay? Because they're their own complex conjugate, they have to be real. All the off-diagonal symmetric pairs. So I always think about square matrices in terms of a diagonal, and then you have pairs that are on opposite sides of that diagonal. Okay, that's what I mean by off-diagonal symmetric pairs. They have to be complex conjugates of each other. Again, from this idea that when we do a Hermitian conjugation, we take the matrix, take its conjugate, transpose. If it's Hermitian, then those two matrices have to be equal, which means those two elements have to be equal. Okay. Hermitian matrices are what we call normal, which basically just means that the order of operating a matrix and its Hermitian conjugate doesn't matter, okay? And that means we're not so fussed with normal, we're more fussed with the implications of normal, which means that it's diagonalizable. And we'll talk a little bit more about diagonalizable later on when we look at eigenvalues in a bit more detail. But what it means is essentially you can take that matrix and you can transform it in such a way that only the diagonal elements are non-zero and all of the off-diagonal elements will end up being zero, okay? And then the last two is that the sum of any two Hermitian matrices is also Hermitian, and the determinant of a Hermitian matrix is real. 4 and 5 are the kind of things that textbooks like Griffith either prove, and if you cleanly follow the textbook in a lecture course, I would bore you to death proving all these things from linear algebra that hopefully you've learned in maths anyway, or you can prove for yourself. And so those last two, feel free to play around and prove them for yourself. They're kind of a nice little exercise just to check that you really understand things. Okay, so I want to finish this half by looking at the key reason why we care about Hermitian operators, and we basically try to push all of the non-Hermitian operators out of what we do in quantum mechanics. The key reason for it is that the eigenvalues for a Hermitian operator are always real, okay? And this is actually a nice little piece of maths to do, so I'm going to work through this one. So that means I'm going to need some paper. I'm going to work through this one for two reasons. One is it's good to know, to have seen this idea of how this works. It's also going to be one of the first sort of look at just handling algebra in quantum mechanics without having specific, specific numbers put into places and stuff like that. Okay. So what we're going to do is we would normally have, we would write our kets as A, and we might take some random number, we would call it Z, okay? One thing that we do with our notation quite commonly is if we're specifically talking about our eigenvalues and eigenvectors, we usually call the eigenvalues lambda, and we call the eigenvectors lambda as well. And this is nothing more than a way for, particularly if we're handling a specific operator, we'll call it by whatever its name. If we're measuring spin, we'll call it sigma. If we're doing rotations, we'll call it R. If it's a projection operator, we might call it some, P or something like that. But if we're just looking at general operators or general matrices, often if we don't care very much about them, we'll just call them A, B, and C or whatever. Numbers, we'll just call them Z or A. If we're talking about eigenvalues, we usually just stick to lambda, okay? So what we know here is, or where we're going to start here is we're going to have a Hermitian operator. We're going to call it L simply because lambda is Greek for L, right? And so what we're going to say is that lambda is an eigenvalue and eigenvector for this arbitrary operator L. So the way we would write this is like this. Operator L acting on the eigenvector lambda is equal to lambda times lambda, okay? And so you'll kind of drive yourself crazy going lambda equals lambda, 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 but you'll get the hang of it quickly enough. Okay, so let's call that number one because we're going to reuse that equation later on. What we know from Hermitian conjugation is that if we want to write the bra version of this, what we have to do is conjugate everything in there. Okay, so what we're going to do is take equation one and we're going to write the conjugate of equation one. So what we would do here is go to the bra form for lambda. We would put the operator to the right of it, because remember it goes on the side where the straight bar is, and we put the dagger in because we're taking a Hermitian conjugate, okay? And then in here we would have our bra lambda, and then again we do the same thing with numbers. We put the number on the side with the straight bracket here, okay? So this would be lambda, and of course it would be the conjugate, so it's that, right? And going from ket to bra, the conjugation's implied. Okay, so one thing we know is that L is Hermitian, right? So what that means is that L is equal to L dagger, right? And so we can take the equation that we just had above and we can write it like this. And let's call this one 2 because we're going to reuse it later, okay? And so now you can kind of see already what I was talking about a few moments ago about sometimes we're a little sloppy about keeping the dagger because if everything's Hermitian, you can kind of drop it and know that everything's okay, all right? So what I'm going to do here is I'm going to take 1, and what I'm going to do is multiply it by the bra lambda, okay? And so what we would now have is when we do this multiplication, what we actually do is we put that element in the place that's right in terms of the angle brackets being on the edges and things being up against the straight brackets. So what this would be is lambda L lambda is equal to lambda lambda lambda, like so. Okay, and you could imagine what I could have equivalently written lambda 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 if I wanted to, but because this thing here is just a number, we know that we can just pull the number out the front, and so that's why I end up with notation that looks like that. Okay, so operators have to stay where they are because they have to operate on something. Numbers that are just multiplicative, you can usually pull them out the front. Okay, so let's call this equation 3 because we might want to use it down below. Just don't number every single equation that you do, particularly in exams, because you won't have the time. Usually it's just worth spotting the ones that you're going to reuse later and numbering those so that you can talk about using them. Okay, so what we're going to do now is take number 2 and we're going to multiply it by the ket lambda this time. Okay, and now what we need to do is the same idea. We need to put things in their places so that the angle brackets are on the edge and they sit in the right places with respect to the bars. Okay, so this would now be lambda L lambda is equal to lambda lambda star lambda, like this. And of course this lambda star is just a number, so I can pull it out to the front as well. So this would be lambda star lambda lambda, like so. Okay, and so just to make this really clear, this this bra here is turned up there, and this ket here has turned up there, and on the end there. Okay, so where we put it depends on what type it is. Bras tend to go hanging off to the left, kets tend to go hanging off to the right. Okay, we can call this one number 4. Now, what you'll notice is that 3 is this thing, lambda L lambda, and 4 is the same thing, lambda L lambda. So if 3 and 4 are true, then that means that lambda 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 is equal to lambda star lambda lambda, right? And if that's true, this thing is this thing, so I can divide it out on both sides. And what it says is that lambda is equal to lambda star. In other words, the eigenvalue is equal to its own conjugate, and is equal to its own conjugate. And as you know from your complex numbers, any number that's equal to its own conjugate can only be the case if the imaginary part's 0, which means it's real. Okay, so, and there's a physical requirement that comes behind this. The physical requirement is that if you have an operator that's connected to an observable, as I mentioned earlier, the eigenvalues represent the possible measurable outcomes, right? Now, when we translate from our Hilbert space back to the real world, you can't have complex outcomes, right? You can't ask, what is the direction of the spin? Oh, it points, into the complex plane. It doesn't make any sense. What needs to happen is that the things that you measure are real in the same way that the probabilities have to be real as well. So anything that comes out of this complex vector space has to come out as a real number. And so this is the main reason why we try to restrict ourselves to Hermitian operators in quantum mechanics. We need the things that pop out of it to be real, those things, the eigenvalues, and as we just showed, the direct implication of an operator being Hermitian is that the eigenvalues it has are real. Okay, that's in the end, the real importance of why we care so much about Hermitian operators in quantum mechanics. I think I'm going to stop there for this one at the moment. and we'll take a short break. And then what I'm going to do is come back in the second half and look at expectation values, which is one, it's an important thing for thinking forwards in quantum mechanics. And it's also another nice example of using the mathematics of operators and vectors so that you can sort of get used to how that works. I'll see you soon.